So we can keep doing integrals. Previously we did double integrals, but you can keep going. You can do triple integrals, you can do quadruple integrals, you can do as many integrals as you want if you're really doing multivariable calculus. We can just do triple integrals we're going to do in this section, but you can do n integrals, okay? So what we are doing now is that we have a function, say f of x, y, z. We have a region in x, y, z, so we have a 3D region, I don't know, some region, and there is a value of a function at every point of that region, and then if this is my region, then I'm going to want to evaluate the integral over that region of this function of 3 variables. And now the d is sort of in volume. What is the value in that 3D region? Okay? This is just what we're doing in 2 variables, just in 3 variables. So let's see, first of all, what are those integrals? First of all, we can start with the easiest case, which is do an integral in a box. Yes, that's a good question. So when we do a double integral, we are adding the values of a function in a plane region, okay? Which you can interpret, for example, as the volume of the function above that plane region, right? But for example, when we do the integral of the function 1, we are getting an area. So the double integral is really doing an integral above, an integral of area and adding values in that area. Just like when you're doing an integral in one variable, it's an integral over one interval, and then adding the functions of a value in one interval, okay? So in one dimension, you are adding values of one variable. In 2 dimensions, you're adding values of 2 variables. In 3 dimensions, what's happening is that I have values in a whole 3-dimensional region, and I want to add all the possible values in that entire region, okay? So if you are thinking, okay, so what is it that I'm calculating if I integrate over a region and I integrate the function f over a region that is in 3 dimensions, you're actually doing some integral that is computing some 4-dimensional volume, right? But the integral itself is running over space. Is what we are doing here, just like we did in 2 dimensions. If I had a region, the simplest regions were boxes, and then I just ran over every point in that box and added all the values of my function f. So now I have to run over every box, every little box in this big box, and sort of like add all the possible values of that function in that box. So first of all, boxes like this, the simplest of all regions in 3D is some sort of box where the x coordinate is going between some interval from a to b, the y coordinate is going from c to d, the z coordinate is going from r to s. And then we're trying to figure out how to integrate that. The Riemann integral, the same concept applies, that I'm going to divide this box into however many cubes, and then in each cube, which will have dimensions delta x, delta y, delta z, in each cube we pick a point at random inside the cube, evaluate the function at that random point inside it, and then add up all these volumes of it's more than volumes, as I said, this is the value of the function times the volume of the box, okay? So all those numbers added up together gives me an estimate of what is the total sum of all the values in that box. And as I do more and more partitions, then I'm getting closer and closer to the actual value of this number. So that is what the triple integral is in Riemann integral. And if you have more variables, you can do this with 3, 4, 5, and as many variables as you want. And what Fubini's theorem says in this case is that I can interpret that volume as an integral, as an iterated integral, where I'm integrating x from a to b, y from c to d, z from r to s, and that under the conditions that f is continuous on that box. By the way, these boxes, a box like this, we call it is the triple Cartesian product from a to b, c to d, r to s. And that means, this means, that is, it includes triples where the x is in the x, the y, and the z are in those intervals between a and b, c and d, and r and s. So if I want to integrate in that box, Fubini tells me that I can integrate as an iterated integral, as an iterated triple integral, and that also I could actually change the limits of integration if it's convenient. So let's see an example where I want to evaluate the triple integral in that box. So if I want to evaluate this triple integral, then I'm going to evaluate from, so the way I set it up in here, z is last, so z appears here first, from 0 to 3 in z, from -1 to 2 in y, and from 0 to 1 in x, of x, y, z squared, dx, dy, dz. And here the most important thing to keep track of is that the order here coincides with the order of the intervals. So this is the bounds, these are the bounds for x, the bounds for y, and the bounds for z. So they have to coincide here and here. And now we can just integrate, as we did with iterated integrals, double integrals, and just one at a time. So now we start, let me just, don't write those limits of integration quite yet. And for x, I'm integrating x, y, z squared with respect to x. So that will be x squared divided by 2, y, z squared between 0 and 1. And then I'll have dy and dz to worry about. So at 1, I get a half, and at 0, I get 0. So this will be the integral now from 0 to 3, from -1 to 2, of, at 1, I just get a half. So I get a half y z squared. And at 0, I get 0. So this is just this, like that. Now I keep going. Now I have to integrate with respect to y. This will be the integral from 0 to 3. With respect to y, a half y, the integral is y squared. So this is y squared z squared between -1 and 2 dz. So that is how much? So I get, so this is the integral of y is y squared divided by 2, so I am actually going to get a fourth in there, right? Thank you. So that is, so I am going to get, let's see, a fourth, 2s squared, and at -1 I get that, so I'm going to get z squared minus a fourth, 3/4 z squared. Now 3z squared, that is the derivative of z cubed, so this will become z cubed divided by 4 between 0 and 3. Yeah. And then at 3, I get 3 cubed divided by 4. So I get 27 divided by 4. And at 0, I get 0. So the answer is 27 divided by 4. So that's a good question. So if I had done that, so the volume of this is 1 times 3 times 3 is 9. Why? Were you expecting the volume to be 9?
No.
So, but the question is, why is there, where's that 9, right? So the answer is that we have a four-dimensional object that is sitting on top of something of volume 9. Just imagine, when I'm saying these words, think of an area of area 9, of region of area 9, and then a function on top that is creating a volume, a total volume of some volume. So there will be 9 in area plus, and then there is some function on top that will give you some volume that we have to calculate using calculus.
Gotcha. Okay.
Here, what's happening is that I have a region of volume 9, and in 4 dimensions, there is sort of like a 4-dimensional thing that is sitting on top of that volume, of that region of volume 9. And now I have to compute the hypervolume of that thing.
Got it.
This hypervolume was 27 over 4. Okay?
Yeah. Okay, thank you.
That's just like if I was to integrate the a paraboloid over a circle of radius 9, you don't expect the answer to be 9. There will be some volume because there is now a function on top. Okay? Yes. By the way, as I said, if I was integrating, if the question was integrate 1 dV, that is the actual volume of the box. Okay, like the same properties in the double integral. If I did over a double integral, the answer is the area of the region you're integrating over. But in here would be volume of my box, and that would be 9. Okay?
Thank you.
The other thing I wanted to mention while we're here is that when I integrated 0 to 1, when I integrated from 0 to 3, from minus 1 to 2, from 0 to 1 of x, y, z squared dx, dy, dz. Remember that if I have functions that are products of functions in x and y in a double integral, I can actually split it up as a product of integrals. So this is, in fact, the integral from 0 to 3 of z squared dz times the integral from minus 1 to 2 of y dy, and integral from 0 to 1 of x dx. And that's because x, y, z squared is a function of x times a function of y times a function of z, and we are integrating over a box. Okay, if the region is not a box, then this doesn't apply. If the functions do not multiply this nicely, and I had an x plus y there, I would not be able to do this. But in that case, I can integrate these 3 things and get the answer. Okay. So we're going to have more interesting regions to worry about. For example, a region of this sort, or a region of that sort. What that means is that in the xy plane, I have what we call the type 1 region. In the xy plane here, I have what I call a type 2 region. And then the z value is between 2 functions of x and y. So this kind of region, let's first try to, let's call this region here E1, and this region here E2. Let's first of all describe the regions. In Cartesian coordinates, those are x, y, z's, such that in a type 1 region, remember that the x coordinate is the one in an interval. So the x coordinate here is going, is going here. for a given x, the y coordinate is between two functions, and for a given x and y, the z value is going in between two functions. So the x coordinate is going from a to b. The y coordinate is between two functions of x, and the z coordinate is between two functions of x and y. So it's between some u1 and some u2. Okay. In the second region, we have that the one to run first is y. Then the x is between two functions of y. And then for any one of those points, the z value is again between a function of x and y and a function of x and y. So E2 here is a Cartesian. Now you can abstract your thought and think that we will do the equivalent of polar coordinates next, which is there's two different types. We can generalize these to what we call cylindrical coordinates or spherical coordinates. So we'll do those. But in x, y, z now, it's the y that is in an interval. The x is between two functions of y. And the z is, again, between two functions of x and y. Okay? So, and notice that this setup is what we called a type 1 integral when we were doing double integrals. And this setup is what we called a type 2 when we were doing double integrals. Well, it turns out that this setup where the region is in the xy plane is what we're going to call type 1 regions in triple integrals. And then if the region is in the yz plane or the region is in the xz plane, those will be type 2 and type 3 regions. Okay, so those are the definitions of the sets that I'm working with. And now I want to set up the integrals. So if I want to integrate a function, I have some function now, f of x, y, z. And I want to integrate it on one of those regions. So this is going to be E1, this is going to be E2. How would I set up the integral? The integral on E1 will be x is running from a to b, so I have to start with x here outside. The y is going from g1x to g2x. And the z is going from u1 to u2. F of x, y, z. And now the innermost is what's happening to z. So this is z, x, y, and x. But on E2, I have to first run in y. So I'm going from c to d and doing dy. Then x is the next one to run from h1 of y to h2 of y, so that is dx. And then the z is going from u1 to u2. dz. Somehow they didn't match up. dz, dx, dy. So that's the two possibilities. And this is what we call, if the innermost integral is with respect to z, we call these of type 1 triple integrals. And we'll see type 2 and type 3 come up. Okay? So that's how you set up the integrals. Let's see. This is a clean version of that. And look again that z is innermost, z is innermost, but it depends. I think there was a typo in the book. This is supposed to be dy dx. Okay, so let's do that. I want to integrate the function z over the solid that is in the first octant. First octant is when x, y, and z are positive. Bounded by the surface, z is equal to 12xy, and the planes y equals x, and x equals 1. So let's see what all that means. So this is x, y, and z. And let's see, they mean that I'm going to be integrating in this region, okay, only in this first quadrant when x, y, and z are positive. I have x equals 1. That gives me an entire plane, okay, that is here in front. Y equals x is a plane. This is the line y equals x in the xy plane, so it cuts another plane like that. Okay, so everything is happening within this prism. And now there is a function z, which is, I don't know what that function does, but it's, I don't know, I'm just going to draw something here. Like this. So whatever is happening inside here, that's what I need to figure out how to integrate. So let's try to do the integral of this. So I'm going to integrate. So here x is going from 0 to 1. Okay, I know that much. So the region is going to be x, y, z. And then so as I said, it's the region that is in here. So first of all, x is between 0 and 1. If I want to set it up as I said, a type 1 triple integral, the x has to run in an interval. The y can run, if I look at my graph right here, let's say here, for a given x, the y can run up to x. Okay, so it goes from 0 up to x. So the y is going up to x. And for a given point here, the z values are going between 0 and this graph that I have, z is equal to 12xy. So the z values are sandwiched between 0 and 12xy. And that's the work, so I can set up my integral. So that integral here, I will be the integral first, the variable that goes in an interval from 0 to 1. The y goes from 0 to x. And the z goes from 0 to 12xy. And I'm integrating the function z with respect to volume. In this case, this is not any polar. I don't have to do any conversion factor. This is just z times. And now the outermost is dz, what equals what? dz, then the next one is dy, and then the next one is dx. All right, so let's do it. This is, by the way, what the region looks like, a little better drawn. So I'm integrating again from 0 to 1, 0 to x, 0 to 12xy, z, dz, dy, dx. So I just do it in order. With respect to z, this is z squared divided by 2, dy, dx. I have to integrate between 12xy and 0. This is 0 to 1, 0 to x, and that will be 12 squared x squared y squared divided by 2 minus the value at 0, which is 0, so this is just dy dx over there. Then it will be the integral from 0 to 1 in y. That will be, so there was an x squared here, and then y squared became y cubed divided by 3 between 0 and x. So this became, this was going to be with respect to x. So this became from integral from 0 to 1 of 12 squared times divided by 6 times x. That would have been x to the 4, 5, x to the 6 divided by 6 between 0 and 1. What's 0 and 1? No, just up to there. Does that make more sense? Did I do this right now? This is 12x squared. The x squared is not integrated with respect to y. Y squared became y cubed divided by 3. All right, so, and so on. So these are the, what we call in triple integrals type 1. If the region we're integrating over, there is a region that we define in the xy plane, and then the z values are sandwiched between two functions. Now, you can flip that image and do type 2 integrals, where the region is in the yz plane, and the x coordinate is the one that's sandwiched between two functions. Or type 3, where the region is in the xz plane, and the y is between two functions. So let me give you some example of those, where we're going to do the triple integral, where E is the solid bounded by the surface, y is x squared plus z squared, and the plane y equals 4. What does that look like in 3D? Now, as we're drawing those quadrics comes in handy, because I have to figure out what this looks like. And x squared plus z squared equals y. If you did sort of like change of variables in your mind, we usually had z is equal to x squared plus y squared, gave me a paraboloid. So this is a paraboloid, but going in a different direction. This is a paraboloid going in the y direction. Okay? So the paraboloid looks like this. Okay? This is y is equal to x squared plus z squared. And then the plane y equals 4 comes in here. If this is 4, then the plane y equals 4 cuts out a plane like this, and it just sort of like stops this paraboloid like this. Okay? So inside that section of a paraboloid, that's where we are integrating. So I'm going to describe the region then. The region is, what is happening? I have to describe the region, first of all, by describing what is happening in the xz plane. Okay, the projection on the xz plane is a circle. So if I want, I can do, so I can first describe what's happening here, and then the y coordinate is going to go in that region. So for example here, I can describe the x between, so what circle is this, by the way? What circle is that going to be? It's the same that we get when I cut out x squared plus z squared is equal to 4. So that is a 1 of radius 2. It's a circle of radius 2 in the xz plane. And I can describe that in x, for example, is radius 2. So the x goes between -2 and 2. the z value will go between, z is 4 minus x squared. If I try to describe what the z value is from this circle, is 4 minus x squared square root and plus minus. So the z value goes from minus 4x squared to 4 minus x squared and then square root. And then the y coordinate, so it is actually between x squared plus z squared and 4, because it is in the inside, not the outside. That is the integral. It would be the integral for x from minus 2 to 2. The integral for y between the square root of 4 minus the square root of 4 minus x squared to the square root of 4 minus x squared. And then the integral from x squared plus z squared to 4. And now it is the integral of x squared plus y squared, the z, the, this last one is the y that is going, then it is the z, and then it was the x. So we are in the inside of the, so somewhere from here to here for the ranges. So it is going from the paraboloid up to 4. The z value is going from an x to from here to here, so from a half circle to a half circle, and the x is going from minus 2 to 2. This order? That's a good question. So so the order was the way I determined in what order I was describing my my region. So I described my region as x goes from minus 2 to 2. I could have started with z if I wanted and say z is going from minus 2 to 2 and then tell you what x was. But my choice was I'm going to do x from minus 2 to 2. Z is going anywhere from the half circle, the bottom half circle, to the top half circle. And the y is going anywhere from the paraboloid to the plane. So it has to be that x is at the very end, because it corresponds to this integral. Then I'm doing the z values, and then I'm doing the y's. So if you go back to how you naturally describe this region, any point in here is, or any one of these, and then any one of those, that should be the order in that direction from here to here to here. Okay? Now, this seems like it's going to be a lot of work, and it is going to be a lot of work to do this, but if you look at your picture, or you look at this picture right here, there is some very nice symmetry, radial symmetry, with respect to the y-axis. Okay? What that means is that in our favor, we should translate this into what we call cylindrical coordinates. Okay? So I'm not going to do this now, but what we're going to do is let's wait, and let's not do that right now, because I'm going to translate into cylindrical coordinates. All that I'm actually going to do is that I would translate this into polar coordinates. So the x and the z value has to go into polar, and the y can remain as it is. But we have to learn what is going to be the conversion factor. It will be the same, but we will do that when we learn about cylindrical coordinates next time. This is a type 3 integral, because the region we started from is in the xz plane. So I read it as a type 3 integral. In that type 3 integral, there is a region in the xz plane, and then it moves into the y coordinates. It matters like what the integral is going to be like. I don't remember the names of type 1, type 2, type 3. I just describe my region, and then what matters is what we did here. Like, what is the limits of integration here and here, And that just comes from how we are defining this, that I start with a region here and then go that way. Oh, well, that's a good question. So if I in here, these two equations or these two inequalities are describing a circle. So I have, in the xz plane, I'm describing the cross section that everything is above, and that is a circle of radius 2. And here the x goes from 2 to minus 2. If I did what you're saying, I would be describing a square in here. But I don't want to integrate over a square. I want to integrate over a circle of radius 2. All right. So we'll come back to this. So now what I would like to do is reinterpret this integral in 3 different ways. So we'll practice this changing from one type to another with an area of the region that can be interpreted in all 3 ways. So we'll do that next time.